So let's recap this one more time. If a force F compresses the spring by a small distance dx, and during that small displacement dx, we would assume that the force remains a constant, and the work done to do that is F dx. And if now the spring is compressed from a position x equal to x1 to a final position x equal to x2, the total work done can be obtained by integrating this quantity. What quantity? F dx, the small work done, can be integrated from x equal to x1 to x equal to x2. So the total work done is integral x1 to x2 of f dx. And what is our f equal to? F can be replaced by what quantity? Kx. So that will be integral x1 to x2 of kx dx. K is a constant that comes out. That will be integral x1 to x2 of x dx. And integral x dx will be x squared divided by 2. And now apply the lower limit and the upper limit. What does that become? It will be k over 2 times x2 squared minus x1 squared. Now, if this x1 is 0, that means we started with initial displacement 0, and this x2 is called x, then the work done to stretch a spring by an amount x can be written as 1/2 kx squared. Alright? So this expression will reduce to this when x1 equal to 0 and you call x2 equal to x. The amount of work done to stretch or compress a spring by a distance x is 1/2 kx squared. On the other hand, if you want to stretch it from an initial value x1 to a final value x2, the work done will be 1/2 k, which is the same as this. Instead of x squared, you have x2 squared minus x1 squared. We will now use these concepts to solve problems. Let's start with this problem. A particular spring has a force constant of 2.5 times 10 to the 3 Newton per meter. How much work is done in stretching the relaxed spring 6 centimeter? Well, the relaxed spring means your x1 equal to 0. You got to stretch the spring by a distance x equal to 6 centimeter. Well, straightforward, is that right? And how much work is done in stretching the spring an additional 2 centimeter? Alright, let's put down the values we know. The force involved in stretching the spring is identical to the force required in compressing it. So we will use one for the other without any problem. In part A, the spring is stretched from an initial position x1 equal to 0, it's a relaxed position, to x2 equal to 0.06 meter. So x1 equal to 0, a force F stretches it to x2 equal to 0.06. So it is this displacement that we call 0.06. Work done is 1/2 k x2 squared minus x1 squared, where your x1 equal to 0. And you use all the values. K is given to us, and x2 we know, x1 we know. That is 4.5 joules. Alright. Next, how much work is done in stretching the spring an additional 2 centimeter? Well, the spring is now stretched from x2 equal to 0.06 to x3 equal to 0.08. That means it is now stretched from x2 equal to 0.06 to x3 equal to 0.08. Now, therefore, work done will be 1/2 k x3 squared minus x2 squared. And now use all the known values. x3 is 0.08, x2 is 0.06, and that gives you 3.5 joules. You can see the additional work needed to stretch it by this much is much greater than the initial work. That means as you keep stretching the spring, the amount of work you need to do to stretch the spring by the same amount keep on increasing. Why? Because the force keeps on increasing. Another one. A student suspends, now do another problem. A student suspends a 0.25 kilogram mass on a spring and it stretches a distance of 5 centimeters to its equilibrium position. The student then pulls down the suspended mass, doing 6 joules of work in further stretching the spring. How far is the spring stretched as a result of the pulling down by the student? Well, what we have is the case of a spring and the student suspends a mass. Now, what is the stretching force here? The stretching force is the weight of this mass. All right, let's write that down. What is the weight of the mass? The mass is 0.25 kilogram. So its weight will be 2.45 Newton. Now, this 2.45 Newton stretched the spring by how much? The 2.45 Newton stretched it by 5 centimeters. What does it help you to find? Now, you know that the stretching force F equal to kx. This helps us to find the value of k of the spring. You see, in the problem we need the value of k. So let's find the value of k. The displacement produced by this force is 0.05 meter. This is the relaxed spring. And now when we suspend a mass or applying a force of 2.5 Newton produces a displacement x equal to 0.05 meter. Therefore, k, remember, F equal to kx, or k equal to F over x. F is 2.4 Newton, x equal to 0.05 meter, and therefore the k value for this spring is 49 Newton per meter. So the first part of the problem helped us to find k. Alright, let's now take the second part. From the equilibrium position, the spring is stretched a distance x in doing an amount of work W equal to 6 joules. Well, if this is the equilibrium position, now we're going to say x equal to 0 now, and the student applies a force doing a certain amount of work. How much? 6 joules of work in stretching the spring. We need to find how much is the spring stretched from this equilibrium position so that that amount of work, 6 joules, is done. Alright? We know the work, we need to find the distance x. So the student does an amount of work in stretching the spring by an additional distance x. Now W, the work done, equal to 1/2 kx squared. And we can now replace W by 6 joules. K is known, and therefore we can solve for x squared. X squared is 6 times 2, 12 divided by 49, and that will give you x equal to 0.49 meter, which is 49 centimeter. Okay. Another problem. Compute the work done by the variable force F versus X graph shown below. That must be very simple, because work done is a measure of the area enclosed by the graph of F versus X with the x-axis. But one thing you need to know to do this problem, and that is, if an area measured above the x-axis is positive, the area measured below the x-axis is negative. So there are two triangles here. The area of the triangle above the x-axis is positive. The area of the triangle below the x-axis is negative. Work done is given by the area enclosed by the graph of F with the x-axis. Now this area is made up of two triangles, one above the x-axis and the other below the x-axis. The area measured above the x-axis is positive, and the area measured below the x-axis is negative. Let's measure these areas. What is the area of the first triangle? Well, area of a triangle is 1/2 base multiplied by height. Now what is the base here? Base is 2 meter. What is the height? The height there, this is 2, 4, 6. The height is 6 Newton. So that will be 1/2, base is 2 meter, height is 6 Newton. That will be 6 joules, that is positive. And area of the second triangle is, of course, that would be negative, is that right? That will be 1/2, base is, what is the base? 5 minus 2 is the base. And what is the height? Now look at the height of the triangle. The height is negative 6. Negative 6. So that will be negative 9 joules. Okay. The area of the top triangle is positive 6 joules. The area of the bottom triangle is negative 9 joules. And therefore the total work done is the sum of the two. 6 joules minus 9 joules equal to negative 3 joules.